And greetings and welcome, friends. Continuing our look at measures of variability, right? Finding ways to describe how our data is distributed, how it's densely populated in different areas. Today we're going to look at what's called standard deviation. All right, it's very similar to mean deviation. It's a type of it, but it's not quite the same. There's just some tweaks to it, essentially, is what happens. But standard deviation looks like this. All right, so we're going to talk about this formula, but it's measuring the same sort of thing. It's a type of average distance from the mean. Okay, so here we go. Standard deviation. If a set of data has n values, right, given by xi, such that I rather is going to be between 1 and n. So basically, x1 represents your first value, x2 represents your third. We've seen this before. With an arithmetic mean called x bar, right? We've seen that use before. Then the standard deviation. So this being called standard deviation, it is more commonly used than mean deviation. So it is the preferable one. And standard deviation is denoted by a lowercase sigma. It's kind of like this weird little loop with a side tail on it. So that's the lowercase sigma, can be found as follows. Let's see. I'm getting some lag here. Oh yeah, it's lagging. Give it a second. Come on, computer. You can do it. Oh dear. Oh, is it the lag or is it my tablet? Maybe it's the tablet. All right. And I'm back. Haha. Let's see. Can be found as follows. And get ready for another crazy looking formula, but these formulas make sense. All right. So little sigma, standard deviation, is equal to, ready? I guess I'll write the square root. So there's going to be a square root of this whole thing of 1 over n. We've seen 1 over n before, times the sum, the sigma, of I equals 1 to n. And I'm going to have the difference between my data and the mean, but instead of absolute valuing it, I'm going to square that. All right, so that's squared. So this is actually going to be very similar to mean deviation. Actually, in some books, side note, absolute value of x, is actually defined as the square root of x squared, because that will always end up being a positive value, because squaring even a negative number makes it positive, and then square rooting it brings its magnitude back down to normal size. So notice I have the square root of, right, if I was to distribute the square root over the multiplication, the square root of this square kind of will represent the absolute value. So the only real difference is that we'll end up having the square root of n in our denominator, which makes that value smaller, but by dividing by a smaller number, the standard deviation will kind of end up being larger, so to speak, than mean deviation. So it's similar in concept, not too different. So let's talk about implementing this in Excel with a data set. So here we have our list. These are all small values, apparently. And here I've got the absolute values of their differences from the mean, right? I've added those all up, divided by 12, and I found mean deviation like we did yesterday. So in this case, instead of finding the absolute value of their differences, I'm going to square their differences. All right? So I'm going to want to calculate x minus x bar squared, right, is what I'm going to want. So for my formula in Excel, I'm going to say equals, and I want this to equals this guy squared. And that's how I'd program it in Excel, just like that. And so I square those differences, right? Drag that down. Bam. So notice these are significantly larger than their absolute values squared, but these are also all positive. All right, so once I square those differences, what does the formula tell me to do? What's the sigma mean? Add them up. So let's see. Let's find equals sum, and I'm going to add from F3 to F103. Oh, that did not work at all. F103. So it's going to work with a list of up to 100 values for our spreadsheet. And I find the sum is 117. Notice that sum is bigger than that. Actually, theory, would that sum equal this one squared? No, it wouldn't. I just thought of that. No, 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 no. Because that would be squaring over addition. It does not work that way. But anyways, so here's our sum. Let's see. So what do I do after I have that sum? I'm going to multiply by 1 over n, or I guess I could say divide by n. All right, so I could call this, let's see, 1 over n times x minus x bar squared. All right, is what that's going to be. So I'm going to take this. Actually, no, I lied. I lied, didn't I? I want to take this number and multiply by 1 over n. And actually, maybe I'll just square it all together and just calculate the standard deviation. So this is going to equal $f $1. I'm going to divide by n, right? And I think I have n over here being calculated, so that's $a $1, if I'm not mistaken, right? And then the standard deviation also requires me to square root that afterwards, right? And in Excel, to square root, I think it's sqrt. Yep, and you can see that there's the square root function showing up right there. And I get that. So I get 3.13, and that's an absolute reference. If I wanted, I could drag this down and see that the standard deviation will always be the same, right? That's what I want. So notice comparing standard deviation to mean deviation, it is going to be a little bit larger because that basically the n gets square rooted before dividing by it. Now it turns out Excel actually already has a standard deviation formula, which is STDEV, that's what it is. So it's not some sexually transmitted disease formula or anything, it's just standard deviation. And I could actually just have it calculate from A3 to A103, like that, and notice it calculates standard deviation. But you might say, Mr. Waddy, that's different than the one we had, and I would say, I agree. It turns out this formula is being calculated. Notice if I actually do, I believe n, is it -1? No, it must be the +1. Well, that's not quite the same either. But basically, their standard deviation, this formula, is for calculating or estimating the standard deviation based off of a set of data in a population of unknown size, right? So for instance, if I have a school of 150 students, but I only survey the students in Math 4, right, I could estimate kind of the standard deviation of the entire population, find that average data, whatever I happen to gather, for that unknown population. Excel, fortunately, does also have a formula for when I do know the population, which is in most of our cases, which has a little p at the end of it. So if I do equals STDEVP, notice I get this formula here, and it says, give me the numbers. Show me the numbers. So I'm going to plug in A3 to A103, write my list of numbers, and you can see, bam, that one agrees with the one that we calculated in our text. So we're working with a known population size, right, where I knew I only had 12 values here, but there is a type of standard deviation when you have a population that's larger than that. And it has to do with predicting its value of being n+1 or something like that. But don't worry about that too much. But I just want to point out, we could calculate this by hand. I believe the other math teacher does have his students do that, where you literally would make a table like this on paper, and do it all out. I'm going to share this Google spreadsheet with you. It's going to be great. All right. So there is standard deviation for a list of numbers. Same idea as mean deviation. It's just slightly larger because you end up having a square root of n in there is really the only difference. Now I want to talk about standard deviation in a frequency distribution. And if I have a frequency distribution, you might recall, let's see, standard deviation of the data in a frequency distribution. You might recall I was able to estimate the mean of the data in a frequency distribution. Do you recall why? Anybody? Right, but in a frequency distribution, if I was given data in that form, I wouldn't have actually had my original list of numbers. I would have just known how many were in each class. So we ended up making the assumption that each number in a class was just equal to the midpoint of that class or the class mark. So it's technically an approximated mean. Same idea here. We're going to have an approximated standard deviation of the data in a frequency distribution. And I'm actually not going to take the time to write this all out, but basically in this case, x1, x2, ... all the way to xk are going to be our class marks. All right, so k is the number of classes, not necessarily the number of data values. All right, and then f1, f2, ... all the way to fk are the frequencies of those respective classes. All right. So so our formula for this standard deviation in a frequency distribution, I don't have a symbol for it, is going to be the square root. It's a big square root. You might want to save it for later because this is going to actually have a fraction. I'm going to have in my numerator the sum of I equals 1 to k. So I'm adding up all of these values from my classes. I'm going to have the class mark minus the mean squared. All right, and now notice this mean is actually an approximation as well, multiplied by the frequency. So that's my numerator. And it wouldn't be standard deviation if I wasn't dividing by my n, or the square root of n, and that's why this square root symbol, actually I might even extend it now. It might not be long enough for my sake. I want to make sure this denominator clearly has the square root involved in it. So right, in our previous standard deviation formula, I end up dividing by a square root of n, right, is what I end up having. So how do I find out what n is in a frequency distribution? Well, it's going to actually just be the sum of the frequencies, and that won't be an approximation. That's an exact value. So I'm just going to call this sigma of I equals 1 to k of each frequency. And the square root being over the whole fraction would include square rooting this denominator, and the square root of n is kind of where that's coming from. So you can see that this ends up, working and calculating, kind of doing the same thing as standard deviation for a regular thing, although this is an approximation. So what if I wanted to program this in Excel? What? All right, let's see if we can do this. Here's our other one. I don't care for that anymore. I'm going to bounce back to, this is our old frequency distribution chart, right? And we had frequency distributions. I've got all my stuff floating around here. So I want to calculate, let's see. First of all, I need the mean. This one doesn't have the mean anymore, does it? Let me see, actually. Oh, it does. Aha, genius. Look, it was like hidden in font color the whole time. Bam. There's our X bar. All right. So our approximated mean for my list, is this right? It's just 25, straight up 25. Let me change the number just to see if this is calculating based off of these. No, it's based on, peculiar. Oh, wait. Let me change the number to like a much higher value, like 70 or something. There we go. Okay, so it is calculating off of that list. It's making a frequency distribution. It also is making a histogram and everything like that. But so I've got my X bar, right? Let's see. I think, nope, no, I don't want any smart art graphics. The next thing I'd want to calculate is the difference between my class mark and that mean. And you can see that that's actually what I did here, right? So what's my formula look like? I said take the class mark and minus the mean, the X bar, right? So I did that. All right, next thing I want to do is square that value, right? So I believe that's what I do here, hopefully. So x minus x bar squared, and the formula for that, I just squared the thing on the left. All right, so far making sense. What do I have to do after that? I squared it. I don't want to add it just yet. I have to do one more thing. Multiply it by the frequency. So I multiply it by the frequency. So I took this, multiplied by its frequency, and notice this, I then sigma it. I added it all up. So 12495, bam. All right. So I added it all up, and that's my numerator. My denominator, I want the sum of the frequencies, which I think I already have. Maybe I don't. Is this already the right font color? Bam! Man, this is genius. High five, Mr. Waddy from the past. Good job setting this all up in advance. So here we go. So to find this, I now want to divide those two things and square root it. So I want to divide that by that and square root it. Let's see, was I that smart? Oh, it looks like I was. This is the best. So our estimated standard deviation is this divided by the sum of the frequencies, square rooted, and there we go, we get our estimated standard deviation. Now, I think I actually have Excel's standard deviation pop formula there, where I just took the standard deviation of the actual list, which you don't always have in the case of a frequency distribution. And you can see that my estimate is a little bit off, right? Because I was assuming that each data point was merely the class mark of its given class. So those are going to be shared with you as Google Docs. You'll be able to use those online. But that's the idea behind standard deviation for both a set of data and a frequency distribution. Thanks for hanging out, Internet friends. Bye-bye.